Okay, this is the first lecture for using Gurobi for districting. So the first step, you'll want to go to Canvas and click on districting examples. This will take you to a GitHub repository, and you'll want to download this. So I'll download the zip file. Then I'll go to my downloads. I'll unzip it. Okay. So this is where I'll be working. So then I guess next I need to open up Jupyter Notebook. So once I open up Jupyter Notebook, I'll need to navigate to wherever I've stored these files. So in my case, I just left it in downloads. So I'll go inside this folder, and we're going to go click on starters. So you should be in the districting examples main folder and then starters. And this video is about this first districting example, so D1. So I'll click on that. And this example is all about minimizing population deviation. And so the integer programming model that we're going to code up is the exact same one that we saw in the homework. So we're going to work with Oklahoma. We're going to have an index I for each county. Our input parameters will include the populations of each of the counties. And in our case, we have 5 districts, but otherwise that would probably be a parameter. K is usually used for the number of districts. And our variables, we have a binary variable x, xij, that tells you yes or no, is county I assigned to district number j. And then we have a variable y and a variable z that represent the kind of the lower and upper populations. And so we're trying to minimize the difference between these two populations, the most populous district population and the least district population. We have constraints saying that every county I should be assigned to one of these 5 districts. Next, we have that each of these districts, 1 through 5, should have a population between those 2 values, or those 2, in our case, variables. And then all of these x's should be binary. So this is the model that we're going to code up. So let's go back to this code. And right now, this is actually going to be reading the input file that's in that GitHub repository, but that has the 2010 population. So let's redo this first cell. So we're actually going to use the Jerry chain package to read in the graph, and we'll use the exact same code for that. So, okay, so we're going to be importing, let's see, maybe I'll just copy paste this from our previous network X example. Give me just a moment. So that would have been saved, let's see, here. It was the last example that we did, the one for GeoPandas. Okay. This is what I want. This will be used to read in the graph. Oops, I should have read this from the completed example. Let's see. Okay, this is what I want. So in the Network X lecture, I had downloaded something from Canvas. It was a zip file, districting data 2020 county.zip. And I had downloaded it to my computer and unzipped it. And then we had used or referred to this OK County JSON file. So if you I've already done the Network X tutorial, and you still have that folder or that file. You should be able to just copy paste this over. Let's see if it works for me. Now this county level file is not too big. It's probably, it can be read from file within less than a second, but importing Jerry chain may take just a little bit. Okay, so it read it for me. So maybe just to double check, maybe I can print some information here. So I think previously we had printed, yeah, we had printed these populations. So let me go ahead and print that. So I will insert a new cell in between here. Okay. So I'm looking at all of the nodes. I'm getting the name of the county, which is stored in this attribute named 20. I'm getting the population of the county, which is stored in this attribute. This is the total population of the county. And then just for convenience, I'm taking whatever that population is and assigning it to this other field. So it's just easier for me to refer to pop for total population instead of this P001000001. And then we'll print the node number, the county name, and the county population. Okay. So seems to check out. I think 42 was Payne County last time. Yep, 81,000 people. Okay. So we're going to be building this Gurobi model. So maybe the first thing we should do is import Gurobi. We'll import Gurobi, and we'll import this GRB. Okay. Okay, we've imported Gurobi. Okay, so I want to define a parameter for the number of districts. So this will just make it a little easier. So whenever you do your own code, you can plug in whatever the number of congressional districts is for your state. But for Oklahoma, that we're working with now, has 5 congressional districts. Okay. We'll build our model. And then we'll create all of those create all of those variables from our handwritten model. So we had X variables, these were the assignment variables. So we would have a variable for each node of our county level graph and for each district J. So if I tell Gurobi here that I think of this like so for the X variables, we had Xij. I was for the nodes and J was for the districts. So when I tell Gurobi here that we have K different values for J, it's actually going to initialize them as being 0, 1, 2, 3, all the way to K minus 1. So in our case, this will be 0, 1, 2, 3, 4. Okay, so we'll actually have a district number 0, which in practice, the number eggs usually start at 1. But anyway, I guess if we wanted to, we could change this, but it'll be convenient in the later code just to be able to refer to K. Okay, so we have these Xij variables, and each one of them is supposed to be binary. And then we have these other Y and Z variables that are representing the populations of these districts. I can go ahead and type the interpretations of these things. So xij is 1 when county I is assigned to district J. Y is the population of smallest district, smallest in terms of population. And Z, the population of the largest district. Okay, let's see if this will work. Okay. All right, so our objective is to minimize the population deviation. So let me do m.set objective. The first part will be the objective, which is z minus y. And we're trying to minimize this. So I'll do grb.minimize. Okay. Next, we have that each county needs to be assigned to one district. So I'm going to add a set of constraints, and I'm going to add a constraint for each of the counties, which is indexed by these nodes. So for every I in g.nodes, I'm going to add a constraint. And that constraint is going to say we assign that node I to one district. So on the left here, I'm going to have the sum of those x's. I'm summing over all of the different district J. Okay, that looks good to me. All right, so now we need to impose that the district populations are between Y and Z. So for this first one, I'll say that the population is at least Y. And I need to actually impose this constraint for every one of the districts. So I'll write this constraint for every J. And then right here, I'm going to have the population of a node, which I've stored in this totpop field. And I'll multiply that population by the decision to include node I in district J. So this is kind of the pi times xi, or xij, from our formulation. And I need to add this up over all of the nodes. So I'll do for I in g.nodes. Okay, so I'll do the same thing down here. I'll just copy paste that. And now I'll say it's at most Z. Okay. All right, what I'll do is I'm going to go ahead and do m.update. And this will just, I don't have to do this, but it'll make it to where it won't print a whole bunch of things whenever I run this cell. So it'll immediately add these constraints to this model, as opposed to waiting until it solves to add them. So you don't have to add this m.update if you don't want to. Okay, so it seems to have run properly. So now I can go ahead and solve. So I'll do m.optimize, and let's see what happens. Hopefully this works. Okay, so within 3 seconds, it was able to find that the minimum deviation is about 5,500 people. Okay, so we can go ahead and print that objective value. And then I can also retrieve what the districts are. So for each one of these J's, they will define a district. And then to figure out what nodes belong to a particular district J, I just check for all i's, ing.nodes, for which x is 1. So I can write it like this. So this list right here, this contains all of the nodes I for which xij is at least 0.5. You may be tempted to write equals 1 here, but because Gurobi is using floating point arithmetic, this xij.x, so when I do .x, that retrieves the value that variable is taking in our solution. When I retrieve this, it may not be stored as an integer in Gurobi's software. So even though I've told Gurobi that this should be a binary variable, it's ultimately solving linear programs over and over in floating point arithmetic. So this particular xij variable could be taking a value like 0.9999999 or 1.000001. And so Gurobi will look at that and say, oh, okay, that's 1, that's integer, that's binary, that's what I wanted, and it'll just return that. But we need to be a little bit more careful here when we check it. So a good safe way to see if this is supposed to be 1 is if it's just at least 0.5. And in actuality, it'll be like 0.99999 or something like that, but this will work. Okay, and then I can also check what are the district populations. So for each district in a set of districts, I can compute what its sum is, which I'm just going to look at every node I in the district, and I'm going to sum all of these populations. Okay. So I can go ahead and print this. So for each district J, I can print that district J has these nodes and this population. Oops. I should have said districts. It should be district populations. Okay. So it prints that 5,527 people. We have districts 0, 1, 2, 3, and 4. And we have their populations. Okay. Let's see. So we have one district here, district 1, has just a single node, and it's node 6. So if I was curious what that was, and you'd probably guess which one that is, but we can look at the very top. Node 6 represents Oklahoma County. So that one district just has one county in it. And we can, if we wanted to, we could actually print the names of these counties. So let's see. So we could look at, for all of the nodes in the district, let's see. We'll look at that particular district and we'll see what what are the nodes in here? So for every I that's in that district, we will record its name, which is stored in name 20. Okay. So maybe we could add that here. Corresponding counties or county names are and maybe I should add this blank line just to separate these a little bit. Okay, so now we see that District 1 had just a single node 6 in it, which represented Oklahoma County. Okay. Now it's unlikely that these districts are connected. I think they should not be, but we could check. So, nothing in our model explicitly imposed that these districts were connected. So we have no reason to think that they should be, but let's just check. So for every district in districts, we can use that network X function. Is district connected? Then we could just use that is connected function from network X, and we'll want to pass it not the graph G, but the subgraph of G corresponding to that district. It'll look like that. Let me put some spaces here. A little cleaner. Okay. Oh, I haven't imported network X yet. Okay, so you'll see here that one county or that one district that had just that single Oklahoma County in it, that one's connected because, well, it's just one node. But everything else, all these other districts are not connected. So if we wanted to make sure that these districts are connected, we're going to have to add some constraints. And so that's what we'll do in the subsequent videos.